Hey everybody, so in this video we're going to look at finding moments that are in equilibrium. So when moments are in equilibrium, it means the total clockwise moments about a particular point are equal to the total anticlockwise moments about the same point. In simpler terms, all the turning effects in both directions balance each other out. This results in no net turning effect, and the system remains stable or in equilibrium. And we're going to apply this idea in example 1, where we're told that the diagram shows a uniform rod, A to B, of length 5 meters and weight 12 newtons. The uniform rod is held in horizontal equilibrium by two vertical wires attached at C and D, and we've been asked to find the tension in the wire at C and at D. Okay, so there's a few things to think about here. Because we're told the rod is uniform, it means this weight of 12 newtons is acting halfway along the rod. So we can show this as the distance from A to the 12 newtons will be 2.5 meters, and that is half of this 5. Because it's in equilibrium, it means the upward force, the tension in C and the tension in the wire at D, the total of this force is equal to the total of the downward force, which is the 12 newtons. So we can say then, resolving vertically, the upward force of the tension in C plus the tension in the wire at D will equal 12 newtons. And we'll come back to this later in the problem. So the next thing we need to do is we need to take moments about a point, and because it's in equilibrium, the clockwise moments will be equal to the anticlockwise moments, and we can choose whichever point we like. I'm going to choose point C. So we can say then that the moments about C acting in a clockwise direction, well, this would be the 12 newtons, but we need to find the distance from C to the 12 newtons. This will be this distance here. We know from A to the 12 is 2.5 meters, and we know A to C is 1 meter. So the distance then will be 1.5 meters. So this will be 1.5 meters multiplied by the force of 12 newtons. And this gives us 18 Newton meters acting in a clockwise direction. And if we take the moments about C now acting in a anti-clockwise direction, we don't need to worry about the tension at C because the distance from this is 0. So this will have no turning effect on C. But we do need to think about the tension at D. We can see it's acting anti-clockwise. It's got a distance of 2.5. So 2.5 meters multiplied by the force of TD, which we don't yet know. So we'll just say TD, newtons, and this will be 2.5 TD. And we're told that the uniform rod is in horizontal equilibrium. And this means the clockwise moments about C must be equal to the anticlockwise moments about the same point. So the 18 must be equal to 2.5 TD. And we can solve this equation. So therefore, TD will be equal to 7.2 newtons. And we can work out the tension in the wire at C using this equation. So TC plus TD 7.2 will equal 12. So TC will equal 4.8 newtons. Okay. But to work out this problem, we use the fact it's uniform to find the distance from A to B force acting downwards. We resolved the forces vertically, and then we took moments about a point. We could have chosen point D. I just chose point C. And in example 2, we're going to look at finding a distance. Okay, so we're told that a light rod of weight 32 newtons is held in horizontal equilibrium by two supports, which apply X newtons and 18 newtons of vertical force, shown in the diagram. So we've got the X newtons here and the 18 newtons here. And the force of x newtons is applied at a distance of d from the end of the rod, and that's at this distance here. We will have to find the force of the x and then the distance at d from the left-hand side of a rod, which is here. So because we're told it's a light uniform rod, we know that this 32 newtons will be acting halfway along the rod, which means this will have a distance of 3 meters from the left-hand side. And because it's in horizontal equilibrium, we know the upward forces will be equal to the 32 newtons. So if we say resolving vertically, this tells us x plus 18, the upward force, will equal the total downward force. So therefore, x must be equal to 14 newtons. So for part B, find the distance from the left-hand side of a rod. Well, now we need to take moments. I'm going to choose take moments from x, but we could have taken moments from anywhere along the rod. So we'll begin with the clockwise moments around x. This will be the 32 newtons acting in this direction. Well, we can work out this distance as 3 take away the d. So this will be 3 minus d multiplied by the force of 32 newtons. So now for the anti-clockwise moments about x. This will be the distance from x to the 18. So 6 minus d multiplied by this force of 18 newtons. And because it's in equilibrium, the clockwise moments will be equal to the anti-clockwise moments. So 3 minus d multiplied by 32 will equal 18 lots of 6 minus d. We can expand out these brackets. So 96 minus 32d will give us 108 minus 18d. We'll move the negative 32d to the other side, and this 108 to the left-hand side. So we get negative 12 is equal to 14d. Then multiply both sides by 14, so d will be equal to negative 6 over 7. And it's a negative because we're looking at going in this direction. But going in the other direction, it will be a positive. So what we'll say then is that d is 6/7 of a meter. Okay? And in example 3, we're going to combine what we did in example 1 and in example 2. Okay, so finally, we're told that a uniform rod AB of weight 36 newtons and length 8 meters sits horizontally in equilibrium on two supports at C and D, as shown here. And the reactions of the supports on the rods at C and D are RC and RD. Given that RC is equal to 5RD, work out the length of X. So perhaps you want to try this question yourself. You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back if you had a go. So because it's uniform, we know this 36 will be acting halfway along the length. And this will be 4 meters. And we know because it's in equilibrium, the upward force is equal to the total downward force. So RC plus RD will equal 36. And we're told here that RC equals 5RD. So we can replace this RC with 5RD. And then we can add these like terms together. So 6 lots of RD will equal 36. So RD must equal 6 newtons. We can put this back into here, and this tells us that RC must equal 30 newtons. So now we've got our upward forces, we can take moments about a point, and I'm going to choose to take moments about point A. So we'll begin with the clockwise moments about A. This will be the 36 newtons, and we know this has a distance of 4 meters from A, so this will be 4 times 36, which gives us 144 Newton meters. For the anti-clockwise moments, well, this will be RC and RD. We're told that RC acts at a distance of x, so this will be x times RC plus RD, which is the distance of 5 meters from A. So this will be 5RD. We know that RC is 30 newtons and RD is 6 newtons. So this will give us 30x plus 30. And because it's in equilibrium, the clockwise moments will be equal to the anti-clockwise moments. So 144 newtons will be exactly the same as 30x plus 30 newtons. We can solve this equation, so 114 will equal 30x. Divide both by 30, so x will be 3.8 meters. Okay? Well, thank you very much for watching. I hope that's given you a clearer idea on how to find moments from a system that is in equilibrium. If you did find that helpful, please like and subscribe, and you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again, and take care.